U is the point that represents the mean position of the mass. Well, in other words, it's the point where all your weight is centered. Or it's your balance point. That's a good way to think of it. It's handy to know what center of gravity means and how to find it. And it's really very easy. Once you understand, you can do some neat tricks for your friends. We can try some experiments today to figure this whole thing out. And all we'll need is a meter stick or a yardstick, some paper, some string, a ruler, and some thumbtacks. Let's start with our meter stick or our yardstick. Do you think I could find the center of gravity of this stick with my eyes closed? It's easy. All you have to do is balance the stick on two outstretched fingers like this. Close your eyes and slide your hands towards each other slowly. When your hands meet in the center, open your eyes and you'll find out that your fingers are on either side of the exact center of this stick. This is the center of gravity, or the balance point of this stick. I can balance it just like this. The weight is equal on both sides of this point. Let's look for the balance point of a piece of paper like this. Now this is a square sheet of paper, so there's an easy way to do it. All you have to do is take a ruler and a pencil and draw diagonal lines from opposing corners of the piece of paper, like this. The point where these two lines cross is the center of gravity of this sheet of paper. You can take a pin, push it right through the center here, and it'll spin nicely on that very same point. Now what if our sheet of paper were shaped like this? It's not as easy, but there is a way to do it. You need a string with a thumbtack on one end and a small weight on the other. Push the pin through the corner of the piece of paper. Look for a vertical wall or a corkboard if you have one to nail it up on. Pin this to the wall and draw a line that matches the string on the piece of paper, just like this. Do this for two other corners of the piece of paper. Any three corners will do. And when you're done, the point where all three of these lines intersect is the center of gravity of this very unusually shaped piece of paper. We'll be back right after this to try some more gravity fun. What we know about the center of gravity, we can make our own pet butterfly. It'll land on your finger or even on your nose. All you'll need are some sheets of construction paper, a couple of round toothpicks, and some tape, some glue, and maybe a couple of dimes or small washers. The first thing you have to do is draw your butterfly. Draw it on a folded piece of paper like this. Draw one half of the butterfly. Make the wings larger than the body of the butterfly. This is important for later on. Now you can cut out your butterfly, and when you're finished, it'll look just like this. Now this is a good point to decorate your butterfly with crayons or marking pens, but try and make him symmetrical. Whatever you put on this side as well, just like in real life. When you're done decorating your butterfly, turn him over and tape a toothpick right in the center of the butterfly with about a half an inch of toothpick showing above the head of the butterfly, just like that. Now, here's the tricky part. You have to take your small washers and glue them to the front of the wings of the butterfly. They should be in the same point on the wing on both sides of the wings, just like this here. There you have it. Your butterfly is all ready for a test flight. Pick him up and see if he'll balance on your finger, just like that. He works because the toothpick represents the center of gravity for the butterfly. On our next show, we'll be investigating the laws of inertia, a property of all matter, including you. And all you'll need are some strips of paper, some coins, and an empty water glass. I'll see you then. On a fully set table, utter a few magic words, and pull the cloth out from underneath the table? Well, there's no magic to it. Just the laws of gravity and inertia. And there's a big difference between magic and science, and this is science. Sir Isaac Newton, an English scientist who lived during the late 1600s, stated that a body at rest tends to remain at rest unless some outside force comes to act upon it. Well, that's the law of inertia. And once that body starts in motion, it tends to remain in motion in a straight line unless an outside force acts upon it to change its direction or motion. We can demonstrate the law of inertia with some strips of paper, a half-dollar, and an empty glass. Newton's law said a body at rest. In this case, our body at rest will be this half-dollar at rest on the edge of this glass, just like this. For our experiment, we're going to put a strip of paper underneath the half-dollar at rest on the edge of the glass. Now, you remember our magician and the tablecloth? What do you think will happen if I try to remove this piece of paper from underneath the coin? Will the coin stay put, or will it follow the paper? Well, if I want it to stay put, and I do, I have to remove it very quickly so that no force acts upon it. Here's an idea. I'll use a ruler to get really quick action on the paper. Let's give it a try. Are you ready? There. The coin stayed put because of inertia. The body at rest stayed at rest because no force came to act upon it. Let's try a different version of the same experiment. For this experiment, you need to make a paper loop. Roll up a piece of paper and glue it together. Here's one that I made a little earlier. You may need to use 2 thicknesses of paper to make it strong enough to support a coin balanced on top of it. Now, what do you think will happen to this coin if I try to remove this paper hoop? Inertia says that the coin will stay put, and then gravity will take over and draw the coin down into the glass. Let's give it a try. Using our ruler again, strike the hoop from the inside of the glass, like that. And the coin fell down into the glass. Gravity drew it downward. We'll be back right after this to try some further investigations into the law of inertia. Related. Occasionally, some pretty surprising things can occur. In this next experiment, we're going to use inertia to overcome gravity. All you'll need is a block of wood, some twine, some thread, and a pair of scissors. Cut 4 pieces of thread about 14 to 18 inches long with your scissors. Now, tie the twine tightly around your block of wood so that it goes around both sides of the block of wood, like this one here. Now, we need a way to hang this block of wood so it's freely suspended. You might have to take 2 chairs and put a brace across the back and hang it from that. Or if you happen to have a ring stand at home, like I do right here, you can use this. Tie your block of wood up so it's freely suspended by the thread. Tie the thread on tightly. When you're doing this experiment, be careful of your hands. We don't want the block of wood to drop on your hands and give you a bruised knuckle. And I have 1 string hanging from the bottom, 1 string on either side. Now, I'm going to pull very carefully and slowly on this lower string. Which string do you think will break? If you pull very, very gradually, very slowly, keep adding more and more strings to it, the upper string broke. The lower string is still intact. Now, tie it back up one more time. And this time, instead of pulling very gradually, pull very, very quickly. Make a very sharp, sudden motion with the lower string. It's a good thing I had my hands out of the way there, or I'd have a fat knuckle right now. Okay. Once it's tied on there good and tight, take hold of your lower string, your second lower string, and this time pull very quickly, very sharply. And the lower string broke this time. What does inertia have to do with which string broke? Well, when we pulled on the lower string, the resistance of the block to movement caused the lower string to snap. On our next show, we'll be investigating inertia and gravity, and all you'll need for that is 2 corks, a fork, and a wooden match, and some string. We'll see you then.